When solving systems of two linear equations, the elimination method is often easier than the substitution method when both equations are written in standard form. So here we have two equations written in standard form. So they are a system of equations because there's more than one of them. And we're trying to solve for x and y. Now we notice that each equation has two variables in it. Well, in this situation, when neither equation y equals or is written in slope-intercept form, what we can do instead is use the elimination method, where we're adding the two equations together to eliminate one of the variables. Now, this system is set up perfectly for elimination because the x's are opposites, and that's what we're looking for. Because notice what happens when we add these two equations together. These x's cancel each other out, and we'll add the y's, and we'll add the constants. And now we have an equation, an easy equation, with just one variable in it. So this shows how the elimination method can jumpstart our solution so that we get really close to part of our answer. I'll just go ahead and divide both sides by -5. And now we know that y equals 1. But that's only half of our answer. We also need to solve for x. So we're going to substitute this 1 in for y into either one of these equations. Now to me, the first one looks a little bit easier. So I'm going to substitute a 1 in for this y. So I'm going to rewrite this first equation, and we'll get 4x minus 2 times whatever y is, and y is 1. That equals 18. So I rewrote the first equation, but instead of writing 2 times y, I wrote 2 times 1, because y equals 1. Now I'll just work out the math here. And we get x equals 5. Now, when we solve a system of equations, we should write our solutions together. So I'm going to move this y over here. Write y equals 1. So that's one way to write our solution to this system of equations. These numbers are solutions to the system of equations because they will make both equations true. So for instance, if I replace x with 5 and y with 1 in the first equation, we get this would be 20 minus 2, which does equal 18. And if we do the same thing in the second equation, we have -20 minus 3, and that equals -23. So this solution works in both equations. Now this system of equations is also set up perfectly for elimination. Notice when we add these two equations together, this time the x's are not going to cancel out, but the y's will, because they're exact opposites. So when we're using elimination, we want either the x's to be opposites or the y's to be opposites. So I'm going to add these two equations together. 3x plus 1x equals 4x. The y's cancel because they're opposites. And -6 minus 10 is -16. I will just divide both sides by 4 to solve for x. And we get x equals -4. So we very quickly figured out half of the answer by using elimination. Now let's take this -4 and substitute it into either the first equation or the second. Doesn't matter, we'll get the same thing. The second one looks a little bit easier. So I'm going to rewrite the second equation, but instead of writing x, I'm going to write -4. So here I go, rewriting the second equation. -4, which is x, or equal to x, minus 3y equals -10. Now I have an equation with just one variable in it. So let's use our inverse operations to solve for y. And so y equals 2. Now I'm going to write these two answers right next to each other. You could write them as a coordinate pair also, as a point. X equals -4 and y equals 2. So these numbers work in both equations. All right, here we have a system of two equations. They're both written in standard form, but notice that the x's are not opposites and the y's are not exact opposites either. Now we do notice that the y's are almost exact opposites. The only problem is they're both positive. So ideally we'd like one of the y's to be positive and one of them to be negative so that when we add the equations together, they're eliminated. Well, we can get the y's to be opposites by multiplying one of the equations on both sides by -1. I think I'll go ahead and do the second one by -1, just because there's a 0 there, and it might make my explanation a little more confusing if I chose the first one. So I'm going to multiply both sides of the second equation by -1. And when I do that, I get positive 2x minus 3y equals -25. Now hang in there for just a second if you're not sure why I did that, because I think in just a moment you'll see why. Now we're not changing the first equation at all, so I'm going to rewrite the first equation right above the second equation. And now we have a system of equations where the y's are exact opposites. So now when I add the two equations together, the y's will cancel. 3x plus 2x. The y's are opposite, so they cancel. 0 plus -25. All right, we get x equals -5. Half done. Now we'll go ahead and substitute this -5 into either the first x or the second x. It doesn't matter which one. Let's see, there aren't, the first one looks a little bit easier, so let's substitute -5 for the x in the first equation. So I'm going to rewrite the first equation here, but instead of writing x, I'll write -5. So 3 times x, which is -5, plus 3y equals 0. So I just rewrote this first equation with a -5 instead of an x. Let's work it out. So I have x equals -5 and y equals 5. Let's write those answers next to each other so it looks nice. You could also write them as a coordinate pair. And we have the solution to our system of equations. Okay, here we have a system of equations where both equations are in standard form, so we're thinking we'll probably use elimination. We notice that the x's are not opposites and neither are the y's. However, we could change this 2y into a positive 8y by multiplying it by positive 4. So what I'm going to do is multiply both sides of the first equation by positive 4 because that will set it up for elimination. By the way, I could add these two equations together, but I'd still have x's and y's in that equation. What we're trying to do is get rid of one of the variables. So I'm going to multiply both sides of this first equation by 4. If you're not sure why I'm doing that, just hang in there. So 4x plus 8y equals -60. So I just rewrote the first equation after multiplying both sides of the equation by 4. Now I'm not going to do anything to the second equation, just rewrite it underneath the first one. Now we see that these y's are exact opposites. So when I add these two equations together, well, notice not only are the y's opposites, but the x's are too. So this problem turned into a special situation. So 4x minus 4x, well, those cancel out. 8y minus 8y, those also cancel out. leaving us with a 0 on the left side of the equation because everything canceled out. And we add these and we get negative 63. Okay, so wait a second. 0 never equals negative 63. So that means we can stop here and we can say there is no solution. If this is a problem on a computer, you might need to write x equals dne for does not exist and y equals dne. Right, but just to go back to what we did at first, sometimes we need to multiply one of the equations by a number so that we can eliminate one of the variables. Now, after we did that on this one, it turned into this special situation with no solution. And by the way, if you end up with something that says like 7 equals 7, well, that means that there's infinitely many solutions. When you have infinitely many solutions, that would mean that the two lines, if we were to graph these two equations, they're really the same line, so they overlap each other. In this situation over here where there's no solution, well, that means the lines never intersect, so it must mean the lines are parallel because they never intersect. All right, once again, we have a system of equations where both equations are in standard form. So we're thinking we'll use elimination to solve this. Now we notice that the x's are not exact opposites and neither are the y's. When we try to turn this 6x into a 9x, we can't really do that. And we can't turn a 6y into a 9y either. So what we're going to need to do on this one is multiply both equations by some number. And it will be a different number for each equation so that we can get either the x's to be opposites or the y's. All right, now we could turn both of these x's into 54s, but it would be better if we noticed that we could also turn them into 18s, because that's a much smaller number and we'll keep these numbers smaller, and that's always a good thing. Okay, so notice these signs are already opposites. So I'm going to multiply the first equation on both sides by 2. And that's going to turn this negative 9x into a negative 18x. And I'll do something similar with the second equation in just a moment. All right, so I'm multiplying both sides by 2 on the first equation and end up with negative 18x minus 18y equals negative 288. All right, so now I want to turn this 6x into an 18x so that it cancels out with this negative 18x. So I need to multiply both sides of this second equation by 3. 3 times 6x, 3 times negative 6y, and negative 12 times 3. All right, we notice that the x's are opposites. And also notice these y's are not opposites. So when we add these two equations together, these y's are not going to cancel out. All right, but these x's do cancel out because they're exact opposites. But this turns into negative 36y. And then when we add those, we get negative 324. Okay, dividing both sides by negative 36, we get y equals 9. All right, halfway there, we now know what y equals. Now we need to substitute this 9 into one of the y's in the original equations. All right, the second equation looks a bit easier because that negative 12 is a lot smaller than negative 144. We could plug it into either one. We'll get the same answer either way, but might as well choose the easier equation. So I'm going to rewrite the second equation, but instead of writing y, I'm going to write 9. So I have 6x minus 6 times 9 equals negative 12. And we'll do our inverse operations to solve for x. Now we know that the solution to this system of equations is x equals 7 and y equals 9. Those numbers will work in both equations and make true statements. It's also where the lines would intersect if we were to graph these equations. I hope these examples have been helpful. This is Mr. Ela, signing off.